Alô, testando.
Alô, alô.
Quem
Testando.
tá no Zoom consegue ouvir?
Sim, sim, consigo.
Bem, mal, mais ou menos.
Parece que tá normal aqui. Tá tudo bem? Tá dando pra ouvir aí também?
Sim, senhor. Perfeito.
Ótimo. Tá ok.
Oi?
Na verdade, eu acho que era quatro. E é quatro. Eu tô treinado. Forte.
Bom, todo mundo, o pessoal tá ouvindo todo mundo do bingo, do Zoom?
Pode falar.
Sim. Pessoal, só rapidinho dando uma introdução em português. Para quem tem desconforto com inglês, as reuniões aqui vão ser em geral em inglês, mas só perguntar, tirar dúvida, então não precisa se preocupar, todo mundo aqui tá aberto a ajudar, ok? Uh, so let's get started. My name is Bruno Gerotti. I'm a master student here under the supervision of Professor Elcio Abdallah. And it's a pleasure to have everyone here, but also our friends that couldn't make it and are participating online with us. So I would like to welcome everyone here today to the first BINGO-ABDUS meeting. And we are going to have a full week with a lot of activities and things to do. The first 3 days, Monday, Tuesday, and Wednesday, we are planning to have these meetings, presentations, and also lectures, where from grad students to professors, they will present and show their work inside the Bingo project. So it's a great opportunity to learn all the things that we do here, because we all know that in Bingo, we have different branches. For instance, I'm from the theoretical part, but a lot of people do different things here, so it's nice to learn it. Uh, on the following days, Thursday and Friday, we are going to have informal meetings. In these meetings, we're just going to discuss research our project, but in an informal way, just to get to know each other. Because we come from different cultures, we have different backgrounds. We have people from the northeast of Brazil, as well from the south, our friends from China. So it's always nice to get to know each other a little better. So again, thank you very much for your presence here, and I hope you enjoy this meeting, our first meeting. And of course, the first person to speak is none other than our professor, Elcio Abdallah.
Thanks, Bruno. Thanks, everybody who is here to follow our meeting. I hope to give a simple, not technical introduction to the project, a presentation that everybody can see and can follow. And it's a project that started almost 15 years ago, 14 years ago, with conversations uh, uh, with the English group, and then it got enlarged in several directions. The first object to be proposed was the BINGO, baryon acoustic oscillations from integrated neutral gas observations. I will explain later what it means. And this was the beginning of the project, which started actually a few years later with an award from FAPESP. And now we are proposing a second phase, even before the first stage, the first part of the proposal starts. We have already a proposal for an advanced bingo, ABDUS. ABDUS is first name of Professor Abdus Salam, who is is a big figure in the scientific community, and we gave this name in his. Como é que é o contador? Advanced BAO, Baryon Acoustic Oscillations Observations for Dark Universe Studies. So let's see what it all means. The bingo was to observe. Basically, the first idea is to unravel the structure of the dark universe. As I'm going also to show, the universe is composed not only from ourselves and our baryons. We are just 5% of the universe. The remaining 95% is something dark. Two parts of dark that I'm going to show you that are the most interesting, constitute the most interesting unknown, the most interesting part of the universe, completely unknown for us. While it is unknown, and we are going to try to unravel this kind of structure that is in the dark universe structure. We also learned that it's possible to see also other further information from the universe, which are the recently discovered fast radio bursts, very strong signature, very strong signal from far universe, from even billions of light years from us. And the most appropriate object to study is the advanced bingo, which is constituted by quite a new technology, also known from 5G technology, which are the phased arrays. All the projects are supported by a consortium, mainly Brazil and part of China, each time more from the Chinese institutions. And today we are a double consortium that is leading this proposal, which is the largest in, I would say it's going to be for some time, it's almost the largest in the southern uniform, southern hemisphere, with the exception of SKA. But certainly it's the largest in Latin America. So the team is very large, around 80 scientists, I counted, or further 100 co-workers from several branches, from technology to services and everything. I put the name of some of them. Actually, I put just the names of people that are directly connected to myself, that I'm presenting the seminar, but it is not at all the whole set of people who are members also from INPE, from some places in Paraíba, from China, and I need several transparencies to show that. These are the names connected basically with myself as one of the members of the project. The support is, it began with FAPESP, with the São Paulo Foundation for Development of Science. Then there was a big effort from the Paraíba government. Paraíba government adopted the project among its even its political achievements, and it was enlarged by other projects in that region. I will put some figures from that. FINEP is the Federal Bank for Development. From MCTI is the Ministry of Science and Technology. Chinese government is putting a lot of effort, and it is today something like up to now, and in the projects that are going that are being proposed, something like 20% of the project. I don't know exactly, but something like that. And a few other helps that are smaller, smaller to much smaller. Okay, so there are some open problems in cosmology. I would cite, actually, I have cited two of them, which are the main importance. One is the dark sector of the universe, so dark energy and dark matter. These are well, up to now, it's just names of of two things that are unknown, that constitute what it cannot be seen by light. And I would say that the other objective are the fast radio bursts, very strong signs which appeared in the universe, and they are equivalent to 10 to the 18 to 10 to 20 grams of mass transformed into energy, transformed into light or radio. First question to be understood, actually historically, is the question of dark matter. There's a brief story of speculations from actually early, well, I would say 20th century, not 19th century. So that's there were some speculations, but in 20th century, actually, Zwicky was the first who really pinpointed that something was going on. He observed the Coma cluster and saw that objects were running around the cluster at a velocity which was much larger by a factor of 10 than what is expected from the intervening mass. And this was a real indication of some more mass than observed would be inside this cluster. So, and then further observations of galaxies and so on just confirmed that observations from that time to today. Of course, the observations in 1933, almost 100 years ago, were much poorer than we know now. And this was just confirmed that there's something missing in the observations from Jodrell Bank, Green Bank, large-scale structure, CMB observations that I'm going to show later, the structure of the radiation from the universe also shows that there is a component, a dark component, which is called dark matter, which is something unknown but massive that attracts. That's the best explanation that we can have. And the established fact is today that it constitutes 25% of the known universe. So I would take for granted that dark matter is a reality. With this amount in the energy budget of the universe. And in principle, the interaction with visible matter is either inexistent, except for gravity, or very, very weak. This is also a possibility. Many evidences and many candidates from the theoretical side, from supersymmetry to things that I cannot even name because I don't even know exactly what they mean. So super this or light that or little that, they're all candidates from the theory forest. And beside that, nobody knows, no? Also, there are other problems connected with the flatness of the universe. The universe must supposedly flat. This is consistent with the observations. So we have the critical density, what means that the total amount of matter is equal to some kind of critical value, which I'm not defining here, but its value is known. So 5% of baryonic matter plus 27% of dark matter is not 100%. 100%. So something is missing. This is what I call the flatness problem in cosmology. Why it's a problem is not clear now, but it's clear for those who work in cosmology. I will just take for granted from now on. And in the at the verge of the 21st century, some few supernova have been observed. They're very typical supernovae where we know the luminosity and know the redshift. So a new redshift versus distance diagram could be done, just like like was done by Hubble. And what was the conclusion is that the universe is not only expanding, but expanding in an accelerated way. That means I throw something up, and not only it goes up, but it goes up in an accelerated way. What is very weird. And it's unexplained in terms of simple physics. So what people suggested is to put a cosmological constant, just like Einstein did. And this was basically baptized the dark energy. In terms of cosmological constant, it's not really a matter, but it can be mimicked by some kind of matter field beside the cosmological constant. And it constitutes what we call the standard lambda CDM model. Lambda is for the cosmological constant, and CDM code dark matter, which is what was shown before. And it was also called the concordance model of cosmology. So 27% of dark matter, 4% of baryonic matter, and something else pointing to, in principle, a cosmological constant or something more complex, namely dark energy. This is a bad description in terms of theory because this cosmological constant is 120, not 120 orders of magnitude, not times, orders of magnitudes smaller than it would be expected. That means that we know nothing about it. No? There are other problems like why they are the same order of magnitude today, and this is also called the coincidence problem. I will not dwell on that much further, but the question is that the dark matter is getting more and more sparse in the universe, while dark energy is basically constant, and they have the same order of magnitude now today. Why? I don't know. No, there are some expectations, even in terms of our existence in the universe. All sorts of proposal have been done, but the fact is that dark energy is also an observational reality, and the universe is simply being accelerated by this kind of objects, which constitute something between 68 and 70 something percent of the universe. The exact number is subject to controversy, even theoretical controversy, but that's not our problem now. And what is causing the acceleration? Nobody knows. It's the same kind of forest that we saw in the case of dark matter. Very disturbing situation with different objects, different orders of magnitude, and we know quite well this part of the universe, the visible sector, but basically nothing about this dark universe. What's the procedure? The procedure is to go to precision cosmology. Precision cosmology means that we observe differently from a century ago or even decades ago. We can make cosmology precision science by studying the structure of these objects here, the power spectrum, which are 2-point correlators. There also correlation between matter in 2 different points or even in 3 different points. And we can obtain these glimpses of small observations from the outside universe. Sometimes I call this whispers of the universe. These whispers we can collect, and we can go to some kind of conclusion. And this is where this BINGO and ABDUS projects come about. So the idea is to observe directly this radiation, the radiation from those who studied quantum mechanics know that the hydrogen atom can have the pair proton-electron with the spins in anti-parallel or parallel states. And there is a very small, very tiny difference in energy that in terms of radiation corresponds to a radiation of 21 centimeters approximately. And this can be observed. It's very rare, but since the hydrogen is the most common object in the universe, we look at places where there are clouds of atomic hydrogen, and we can, by means of some complicated formulation coming from perturbations of Einstein equations and some quantum mechanics, we can find the difference in temperature corresponding to this amount of hydrogen, and we can see what is the distribution of the temperature in the universe. Is this the only object, the only project that does it? Well, several projects that do the more or less have this more or less the same aim, namely looking at the intensity of the radiation that comes from the outside universe with several techniques and different kinds of observation. But in principle, I put here those that work in radio. We particularly look at the with a certain technique with in the observation of intensity mapping from those emissions from the hydrogen, but there are many other projects in this sense. So BINGO was here, and it will be further improved in the ABDUS project. So what do we have? This we actually collect radiation in terms of horns. This is a artistic picture of one of the horns looking inside. It collects the observations from coming from outside space. So the aims are BAO. What's BAO? The baryons in the beginning of the universe were together and interacting with radiation. So they formed gigantic waves, and these waves are natural rules to measure the universe. And they give us information on the structure of the outside geometry of the universe. So we look at this large-scale structure by means of this intensity mapping, and at distances which are measured in terms of what we call the redshift. How much, since the universe is expanding, the distance is measured by means of the velocity of expansion, which is measured in cosmology in terms of the difference of the wave number or the wavelength of the observed light, comparing from where it was emitted and here. And this number is the natural object that gives us distance. 0.127 to 0.445 means roughly half of the universe, very roughly. We have also some astrophysical phenomena, the fast radio bursts, which are going to be more and more important from now on. We have, well, the observations are from the BAO by, actually it's a single dish, but with it's two dishes pointing to one another by technical reasons, and they reflect the outside wave, the outside radiation into gigantic horns. I mean, gigantic means 5 meters long, 2 meters wide. I will show you later. There are two dishes, so two dishes are mirrors, but they are not actually mirrors. They are actually plates, metallic plates from roughly 40 meters. Today, our aim is to construct 28 horns. There's a system temperature which characterizes the noise that we expect from the system. We aimed at 50 degrees, but have 70. In principle, our Chinese collaborators in CETC, they are targeting at a smaller temperature, 40 degrees in principle, which is a cut, a very large and important cut in the background noise. What is, it's a big plus for us, no? And we have a site in Paraíba, in Brazil, which has little noise, and together with the small system temperature, 50 Kelvin, which is not the actual temperature by technical reasons also, it's equivalent to 50 degree real temperature in some sense. And we hope to get good observations. It is in Paraíba, João Pessoa, Campina Grande, Aguiar is the municipality, and Bingo is just here near the border with Ceará. And here also a map from the region. Aguiar is the place. This is roughly the place. And it was important. This is actually where the observation have been made. There is basically no background. This has been measured years ago by our group. Well, we went there, me, myself, and Carlos Alexander Wunche, who is here hidden. He 10 years ago, no? Almost. Yes, 8 years ago. We went there. We actually, before, we have been in several places in South America. There was a big discussion of whether to remain in Uruguay or not for other technical reasons. But I decided to come to Brazil for several reasons. In Uruguay, it was even chosen a place which was military sports, and this was a bit too much for myself. So we decided to come here, which was an extraordinary decision, because in Paraíba we had, or we have also, the support of the local government in order to work. And in fact, the fact that the place is absolutely clean, this is in fact, this is a mobile phone, probably a mobile phone signal at that time. And we went now, there was a group that went now to see for the extended bingo, a larger part of the spectrum, including here what Abdus can observe. I don't have the figure yet. To few hundred megahertz up to 1,700 megahertz, and it looks very, very clean. So Abdus is basically saved. Now, the site is this one. Actually, it was this one. Now it's worked also. This is an artistic view of what is going to be. And let's go a bit for the motivations. I talked a bit about that. The BAOs are the standard ruler. Namely, there are big waves in the universe formed in the beginning of the universe, and observing them, we have a natural rule that we can connect to the geometry. This is Euclid. I mean, our universe is not Euclidean geometry, does not follow Euclidean geometry, and we can see the differences and connect it to Einstein's equations, and see the parameters that characterize Einstein equations and matter today by means of these observations. Basically that's the hope, no? So the science is fixed. This parameter, which is connected to the BAO, is fixed. And we can go further, looking at several scientific challenges to go on. So you see that the redshift connected to bingo was this one. So these are the distances that we characterize. There are further observational spots. Mainly our friends in China have the Tianlai Observatory, have the FAST Observatory, which is this big one. FAST is the largest radio telescope in the world today. And in the second phase of Bingo, in the ABDUS project, we go down much more here to Z, actually in this direction, larger Z, very easily with ABDUS projects. We have here specialists in separating the noise. Alessandro is going to talk about that. He is our source for this kind of technical work, which is fundamental for Bingo. So besides what we want to observe, we observe many things that are here characterized and that are a nuisance for the project. Namely, they interfere with what we see, beside also the radio frequency interference, which is the noise made man-made, that we have to separate as well. What are fast radio bursts? Nobody knows. Someone detected it. Look at some diagrams observed previously. This person here, Lorimer, he saw some small disturbances in the sky and saw that this disturbance was connected with something which they did not know in the beginning what it was or what it meant, but now it's clear that is an extragalactic, has an extragalactic origin and with unknown causes. And we are working on that. So Bruno, who talked before me, he and other people are working in models for fast radio burst theoretical models, but there are many, as many as there are models for dark energy and dark matter. There are also many models for fast radio bursts, but none of them is the most important or the preferred one. Bingo works in various stages. So stage 0, which are the production of horns and electronics. And this is one of the horns. You see that the size of the horn is this one. This hexagon is outside in the institute. If you go to the entrance of the institute, we used this hexagon, now not anymore. So now it's a part of a museum. This is implanted. We baptized Bingo Uirapuru. This is the Federal University in Campina Grande. It's pointed to the sky. It's basically used for us to learn about sky observations, not yet for scientific objects. The stage 2 of the project constitutes component separation, noise analysis, and further theoretical analysis as the bispectrum. And it aims at constructing the basically pipeline, which is to connect and separate the noise and connect from observations to real objects. There is a stage 3 led by our friend here, Jiajun Zhang, which is basically constructing models and mocks from the numerical side for Bingo and many other activities. And a stage 4, which is theory, which is to use all of this information to make models of the universe. And the theory is manifold, with models, astrophysical signs, connections of FRBs and cosmological parameters and so on and so forth, which is the aim of several works that we have been developing. The high resolution phase, namely the ABDUS project, is constituted by this kind is a different technology, similar to 5G. They are small antennas, 20-centimeter antennas connected to one another by means of a state-of-the-art electronics, and which can have a scope or in frequency which is larger. It has they work as many observations and interference within these observations. And there have been proposals for connecting this with our between theory, experiment, and observations of FRBs. It's a sub-project. Actually, the person here present who has most worked in this business is Gabriel, who is today, he was a master student here. Today he's in, or nowadays he's in Manchester doing his PhD, but he's one of the persons working in this development. And the forecasts of using this kind of small antennas, the Vivaldi antennas, is depends on the size of this object. Of course, depends on the money that we have, and depending on the money, we have only Bingo. This is SKA, and first stage or first project of this ABDUS, and a second project. Actually, there are three stages of the project. One where we just have small spots of what we call outriggers to compare with the original Bingo observations. And there is a second proposal, which is a carpet, let's say, of the styles on the side of Bingo horns. And there is a third proposal, which is a full 40 meters squared carpet of collectors, and but that's much more expensive, no? And more and more we get nearer the billionaire SKA. So you see that if we go all the way, we can pinpoint observations much better than ever before, compared or even better than SKA, which is here the red and what's called this Lila diagrams. So we search for FRBs in ABDUS, and this is also not only, well, actually, this is not only a project to study FRBs for themselves, but also as a means of getting constraints on cosmological parameters. I will not dwell on the details. This is details of the peaks, peak of the observations in terms of the frequencies. It's very technical, but even for Bingo itself, for the first stage of Bingo, we have we have competing capability of detecting the flux as compared with, for example, CHIME, which is the Canadian project. But with ABDUS, we go much further beyond, and we use this outrigger to pinpoint. So there are observations, spot observations, or observational spots for Bingo, and we try to put these outriggers, which are very detailed observational spots on the same background as Bingo. When we put one on the top of the others, we can see the same things, compare, and make an array to have um, um, better observational spots and measure the interference of these two spots and promote the ABDUS phase of the observation. So these are described basically the three sequences of the sequence of three proposals for ABDUS, and this is a detailed design of the unit cell, which in my office we still have this first prototype of the ABDUS, several antennas which can be pointed, and they can observe in a single spot, which is much more detailed than the Bingo project. It's a big collaboration. Actually, this has changed a little bit in conformity. This is an old set of universities and centers where Bingo is located, but we have a bit larger set. Actually, some of them are not yet here, not here anymore, but we have a larger set of contributors with support from this in more detail here, this agencies and governments and research places, which I have to acknowledge. There are further projects connected to, actually they were connected to the Paraíba government. Beside Bingo, we have in nearby, 10 kilometers from Bingo, 15 kilometers from Bingo, there has been proposed, actually there is already a resource in terms of support, real support, that means money, from the government of Paraíba for the City of Astronomy, which is more in the direction of outreach, a School of Sciences, which was, I have proposed it myself, and it was accepted by the local government. The Brazil-China Center. There is a Cosmos Foundation, which is taking care of all of the project at a total cost of 180 million reais, which means $30 million. This is outside Bingo science itself. So this is basically extra money. And the support of those institutions which I have already shown point to a cost up to now of 80 million reais, namely $13 million at today's exchange rates. We have many companies working with us, Autec in São Paulo, CTC in China. This is a huge company. They told me that, well, 54 is one of them. CTC itself has, they told me, 250,000 workers. That was what our colleague there has told me. There's a construction company in Paraíba, and the projects are being made in São Paulo by this company, Ponto de Apoio. Our Chinese collaborators are giving alternatives as well. I told you about the electronics, where they improved the system temperature in 10 degrees, which is a lot. And this is oh, forget about this one, but this is the horn, which is proposed by the Chinese in CETC. And our horn, the Brazilian horn, is made of belts. There are belts coming all the way from the beginning to the end, and the design of the Chinese horn is different. So it is competing but helping in the observation. They are going to work one on the side of the other. So these are the companies, and the inauguration will be nothing to do with today inaugurations, fortunately. It's going to be between May and August 2025. We had a delay of 5 months basically due to bad bureaucracy, but we have overcome that. And I believe that we can begin re-observations in August 2025. That's it. Thank you very much.
Thank you very much, guys. Thank you, Professor, for the presentation. We're going to have just a 5 minutes break because we have some technical issues with the presentation online, and we're going to be back just in 5. Thank you, guys. Verdade. Questions? Sorry, questions to Elcio?
Maybe there are some people online who want to.
Oh, also people online, if anyone has any questions.
Any questions?
Any questions on Zoom? No? One? I don't think so.
Thank you, Professor, for the introduction to the project. My question is about the structure of the bingo. Let's say the mirrors and the backend and all that. It's all already constructed, and what is the status of the let's say of contracting those things and placing
The
in the land?
construction.
Huh?
The what? The construction?
Yes, I mean about the of the if the mirrors and all the other things for the experiment, it's everything contracted and what is the let's say what is the status of placing in the
mirrors have
land?
been actually they're finished. No,
Uh-huh.
they have been finished by means of the construction of petals, which are connected together the same way as FAST in China. So it's the same company that made it. It's a set of petals, aluminum, which are designed by means of well, by, in terms of what has been proposed. They have been constructed by CTC 54, and they are today in the harbor I think it's in Shanghai, waiting for the okay from the Brazilian government since a couple of months, because there were some bureaucratic problems in the embarkation. So this is ready, but in the meantime, also the metal structure, which is going to be the support of the main structure, is also ready in China, waiting to be embarked. So the mirrors are already coming. The mirrors are already coming, but the structure is still in Shanghai waiting for embarkation. The set of, or actually half of the set of um, the horns are already done since long time. They were here in the institute, and they are being sent also to the sites. So part of it is there, just waiting for the structure to be built and um, to be put in the structure. What else? The electronics is being made by the CTC 54, and is coming little by little from China. As far as the infrastructure is concerned, we have a command house, which is there with the energy is provided by means of solar plants is also there. The infrastructure in terms of construction is also constructed. It's also made, basically most of it. Part of the concrete and the structure of construction, physical construction, is still on the way.
Mhm. Thank you. Any other question?
Let's thank you, Professor, again.
Thank you, Professor, for the presentation. Okay, guys, just 5 minutes break and we'll be back. Fine.
Dá para ver a apresentação aí?
Essas coisinhas
So let's go, everyone. Let's get back. And the second person to speak today is our friend Jordani. He's here from the University of São Paulo, but currently he is working in Paraíba, and he's going to talk about his work. It's the bispectrum. So, Jordani, you have the word.
Okay. Hello. My name is Jordani, and I'm working with bispectral with Professor Elcio Abdallah, and I help in other points in the project too here at Paraíba. But I present about bispectrum on 21 centimeter reconstructed maps. So the outline of the presentation is I will talk a bit about what is the bispectrum. Then I will talk about our bispectrum module to calculate this bispectrum, and I will talk. The next is talk about the 21 centimeter data and how we construct this data and the method used to study this data with the bispectrum. And I will show the previous results at now about this data I will show to you. And for finishing, I will take a bit about I'll talk a bit about the next steps for this project. So what's the bispectrum? Bispectrum is a third order of angular endpoints power spectrum. As Professor Elcio taught a bit in your presentation, the bispectrum is three-point functions. And the idea to use the bispectrum is to asymmetries of statistical distributions. For example, in a field theory in your case, our field theory is the temperature field. Then how we do this? We get basically 3 points in one sky map. For example, here I have one as example of sky map here. And we study how these 3 points in these sky maps or in this field, statistical distribution of information in this field are correlated between these 3 points. And with this, we study this asymmetry and see if the distribution has or not non-Gaussians inside this distribution. And the idea is use the bispectrum, for example, to study the distribution of the matter in the universe with the 21 centimeters, and you can look to, for example, dark energy or dark matter informations inside these distributions, these sky distributions. So the bispectrum model, basically we get 3 sky maps, or we have the same sky maps, but 3 points in these sky maps. And we need to solve this first equation here, where we need to integrate in multiples, the L's are the multiples, in this sky map. But the first steps is transform these sky maps to make a harmonical spherical transformation to get these terms here. With the ILMs is the value, the important value to calculate the bispectrum. And here, this part of the equation is we call the Gauss integral. It's the more difficult, this more difficult to calculate for the computer. It's more get more computational time to calculate the Gauss integral. And after we calculate these terms and multiply by these terms here, we have this, we can calculate the bispectrum, okay? We follow the algorithm for Butcher, published in 2016. But to calculate the bispectrum, we have constraints in this calculation to make it more easy to calculate, the Gauss integral. Because the bispectrum is, we need to close a triangle form with these 3 points. Then the constraints are the triangular inequality, where they need to close as a triangle, the multiples close as a triangle. The parity invariance, where the sum of the multiples need to be even. And the rotation invariance, where the sum of the complex part of the multiples need to be 0. These m's here. With this algorithm and this model, you can calculate the bispectrum. And we apply for this work in two simulated data sets. And these simulated data sets, the 21 centimeter part of the simulations are from Flask. The foreground simulations are from PSM, the Planck Sky model. The reconstruction maps are made by fast ICA method, implemented to our group by Alessandro. And all simulations are with the maps with 256 inside. And in this presentation, I will show the bispectrum for equilateral case, where equilateral case, I mean the value of the L's are the equal L1, L2, and L3. The multiples are the same. And I will calculate for the L max equals to 200. Then, because of the constraints, for example, we only have the values for 0, 2, and so on. 0, 2, 4, and to give it to the 200. The data sets, I have 2 data sets here. The first data set is the full sky data set. We have one simulation of the full sky in top left. We have one simulation of 21 centimeters full sky, and we have the reconstruction of this 21 centimeters by fast ICA method, where we can compare the reconstructed 21 centimeter and the 21 centimeter of full sky. The second data set is partial sky, where we see only the bingo region. And this is the mask of bingo, and this is the all foreground informations, as we see in the previous slide for full sky. Here we have the prior information, where we have the 21 centimeters but plus white noise simulated for the bingo. And here we have the reconstructed from fast ICA method, reconstruction of this partial sky of this bigger region, using this input here with the total information. Basically, the idea is we have the total information, we have one prior information to compare, and the method tries to give the more equal to this prior, to remove this the information, all information, separate, reconstruct the information of the foregrounds, and the rest of this information is this reconstruction for 21 centimeters plus white noise. So the results here I show the results. I separate in two plots. The first one is 0 to 100 multipole. The second is from 100 to 200 multipole. And I plot here the bispectral results for the absolute value of this bispectrum. Here, in this first plot, I showed the results with compare the bispectral information for full sky simulation, the first data set. And we see in the red, the 21 centimeters inputted as prior, and the black lines are the reconstructed maps. And we see when the algorithm try to reconstruction, the solid lines is the mean of all simulations. We use 400 simulations to make this statistical analysis. And we see when we in mean, when we do this reconstruction, we lost a bit in the mean. We lost a bit of this information when the map is reconstructed. Then, for example, part of the 21 centimeters can stay, for example, in the foregrounds, reconstructed foregrounds, for example. But logically, it's the mean and the error bars. We see the results are quasi equals. Okay. When we look to the second data set, again, I plot only the absolute values of the bispectra. The red line is the 21 centimeter. The black line is this reconstruction information with white noise in 21 centimeters. And the blue line is the prior entry with 21 centimeters plus white noise. Here we have the white noise in the data, and the white noise sum in the information. And we see when we have the reconstruction, the blue, the black lines, and the solid lines are the mean value of all maps. We see when we reconstructed this curve is more early, more close to the red line. Then the construction, the information can be lost. This information, this is prior, right? This information can be given for the foreground reconstruction. And here we see a domain of white noise, because when we look to the 200 centimeter, this is the crease, the information, the values of the bispectrum, but where we have white noise data, white noise information have domain, we see these more constant lines here. Then for this first result, we see we have some domain of white noise values over 21 centimeters. And when we reconstruct the maps with the FastA method, some informations in mean can be lost when we have this reconstruction. Probably going to the foregrounds values of bispectrum. So then, as the next steps, calculate the bispectrum for the other case. We have two other cases in our work. The isosceles excite case, but we need to fix some points in the code to run it again. And stood the bispectrum for more multiples, not only to 200, but going to 600 or more, or 400 or 600 multiple max value, and run the code with non-Gaussian distribution. It's in progress too. Professor Jajun shared with me some non-Gaussian distributions, and we need now I need to create the maps and made this stood in this non-Gaussian distributions. And I don't put here, but calculate the bispectrum for the foregrounds maps, reconstructed foreground maps, and look if the values are different from the original simulations of the foregrounds. That's it. Thank you.
Thank you, Giordani, for the presentation. Does anyone have any questions for him? For the people who are online, you have to write down on the chat if you have questions.
Hi, Jordani. Thank you for your presentation.
Hello, Pablo.
I have a question about your plots. From what I see, it seems there is a bias regarding the foreground reconstruction, right? If I am understanding correctly, how do you intend to tackle this thing? What is the cause of this bias?
Okay, that you mean this difference here, right? When we reconstruct the information, the black lines and the prior information, the blue lines, they are shifted. I need to discuss it with Alessandro, because I don't know exactly how this reconstructed method works as well, right? But while I understand about this reconstruction map, the method tried to reconstruct the foreground information. And the information of 21 centimeters and the white noise are less than the foregrounds. Then the order of this value is 10 to minus 9 or 10 to minus 10. Then and the foregrounds are big values, right? And the order of the bispectrum is bigger. Then when the code tried to reconstruct it, this bispectral information, this is uh, not big value for the bispectrum. Then when they try to reconstruct it, they can get a little bit of this information and pass it to the foregrounds. Probably not see this difference in the foregrounds, because these values are low values. I respond to your question.
Yes, and I think it will also be interesting to see the plots without noise. I don't know why you were plotting plus. Maybe you could remove the noise average to see if you can.
Yeah, here, for example, this one is without noise. We don't have noise in the full sky maps.
Yeah.
We give to me, for example, maps, flash maps with only 21 centimeters information, and this is the result. We lost some information here too.
Yeah, and this foreground bias, I don't know if you are planning to use additive and multiplicative the biasing. I think Alessandro know this technique that could be applied. Are you intending to use this debiasing with multiplicative and additive terms?
Okay, I don't discuss it with him yet, but it's a good question. I will discuss with him about it, about this, the biasing to lost the less information when we reconstruct the maps.
Well, thank you. It was a really nice presentation. Yeah, I finished my question.
Jordani, there is
Thank
a
you.
question on the chat. What is the unit of B figure in your? What's the unit of B in your figure?
Okay, I'm sorry about it. The BL here is the millikelvin cube, because the maps are in millikelvin here. Then it's millikelvin cube.
Okay, thank you. Any more questions? No? Okay, thank you again, Jordani, for your presentation.
Okay.
Now the next person to speak is our friend Alcides. He's gonna talk a little bit about his job is the interaction between dark matter and energy. And he's gonna do a quick overview because we have to keep inside the schedule. So Alcides.
Hello. Hello, everyone. Thank you for your time to listen to me today. I'm Alcides. I'm a master degree student here in USP. And today I talk about my work a little bit. And I work with perturbation with dark matter and dark energy. About the overview, I talk about my work the Lagrangian network, the spin connection, the class, it's a software, and the next steps. My work, why is important in my work? Our structure of the universe depends for dark matter and dark energy. So we understand how it's a behavior from dark matter and dark energy. We can understand how the universe expands in your behavior too. So this is important for the bingo in the cosmology. So about my Lagrangian, it's three parts in here. The first one, and this part, it's a tachyonic field in here. This part is a fermionic field. And the last one, it's a part of perturbation. Okay, we understand how it's this part here because it's a complicated part to make the math and the plot in the class. The tachyonic field is a relationship as relation of dark energy, and the fermionic field is dark matter. It's about spinors. It's complicated to define spinors a little bit, but spinors, actually, we can understand how the behavior of the spin. Okay, so to understand how it's the spinor, you need to use the Clifford algebra in here. No, not all Clifford algebra because it's a little hard. It's many things to understand, but you need to understand Clifford algebra to make spinor calculus. Why we need spinor calculus? Because we need a spin connection to make the math of the fermionic field, because the fermionics, your behavior, it's not equal with baryonic particles in the field, gravitational field. So for these so for this, you need to change our metric, our J mini. It's you need to use the spin connection here, and this is Minkowski. Okay, so my new metric, you need to use this one in here. Okay. So I have many calculus to do. My work is a theoretical work, and in part I calculate tensor, torsion tensor, and contortion tensor here. So and applying this calculus and the ice equation, and here I need to use the Clifford field, this part in here. It's a sigma squared in here. This is positive because my universe is accelerate. So this is positive in here. And Jericho matrix here, it's a Clifford field, Clifford algebra I need to do for resolve. So I calculate some density and pressure in here. The first one is for tachyonic field. The second one is for fermionic field. In the class, I put only for the fermionic field in the because I don't need it for the class tachyonic field, so only fermionic field. So it's only part for the class. It's a big code, has 2,000 lines, and it's the only part for background. We have another part for perturbations. So we need create another new functions inside the class to make our results. So I want plot for for the class I'm doing. And then the next steps, I need to study perturbation report class. I don't know a lot of things in here. In better understand the class simulation. Why? Because I don't know exactly what it means this top and down, top and down. I need a student how it's behavior here. So to explain more. So there is, thank you.
Thank you, Alcides, for the presentation. Does anyone have any questions for him? Gabriel.
I thank you, Alcides. You just showed us that you calculated a torsion and a contortion tensor for your geometry, but are these the same torsion and contortion tensors that we derived in general relativity and we found out that for our space-time they are zero, but here you have something. So what are the consequences of this?
Because it's zero, you
Yeah, because originally they are zero, right? But here it seems that they are not. But I'm not sure if this is the same torsion tensors that I'm thinking from general relativity. Maybe it's just the same name, but they are different.
maybe yes. I don't know actually, but I think it's a kind different because when I have some math, I think it's a error for the paper when I use. I show the professor also because I think they use this you're talking about. It's about the sign. They use a minus sign. I need to use for plus sign. Maybe it's just a sign. I don't know. I
Okay, yeah. No worries. It's just because when we are deriving the Einstein's field equation, right? We are setting that the torsion tensor are zero because the space is not having any kind of torsion,
yeah.
right? It's just bending, etc.
Yeah.
But here you have the torsion and contortion tensors. So I was just thinking about this. But yeah, okay.
They have a different matter.
Oh, okay.
Comes from the matter.
Okay, yeah. Well, from the Lagrangian, right?
Yeah, yeah. This extra term comes from the matter Lagrangian.
Yes. Yes.
Okay, fair enough then. Okay, yep.
I need to work function. Make the work function. From Lagrangian. I have this.
This acts like a repulsive force, right?
Yes.
This sigma is a constant.
Yes. There's a constant. There's a positive. Dirac matrix. It's a little hard to make the math here. All my time in the master degree, basically, it's try to resolve that.
Okay, thank you.
Thank you. É hora do almoço agora, Geraldo. Any question in the Zoom and or YouTube?
Okay, so thank you, Alcides, again for your presentation. And we're a lot of claps. And we'll be back in 1 hour and a half at 1:30 p.m. So you guys can have lunch and we'll be back here in this time, okay? Thank you very much. Also, people from the Zoom, we're going to use the same link, so you might as well connect to that. Cheers.